Hello folks, and welcome back after something of an absence to our next crazy Tesla adventure. Now you may recall in some of the past videos I've said, really guys, can you not give me more of a challenge? I'm so flippin' brilliant, I can do anything, Tesla's easy. Well, yeah, I was wrong about that. So yeah, they kind of got me a little bit. So what I want to talk about today is the bus bar current sensors used in the Model S inverter. Now you may recall that I had rather confidently proclaimed that they were simple analog output sensors. We give them 5 volts and ground, and they give us a 2.5 volt signal that varies each side of the 2.5 volt level depending on whether the current is positive or negative through the relevant sensor. Well, that's kind of not incorrect statement. It does that, but it does it in a rather different way. So let's go have a look at the little test that I've set up on the bench here, and I'll walk you guys through what actually goes on. Alright, so I have basically taken the bottom of the inverter apart here and just removed one of the current bus bars with the current sensor. And I have it set up here in isolation on the bench, and we're feeding it with some 5 volt power supply, and we're looking at what comes out. Now, looking at the multimeter screen, you can see, oh yeah, look at that, Damien, that's that's the 2.5 volt signal, and that's what I saw, and I confidently then proclaimed that we had an analog output current sensor. Well, after some investigation, wrong, really getting it all wrong these days, we can see that it's kind of not analog, it's digital. What you are looking at there is what is called a delta sigma analog to digital converter, and basically on the sensor board here there's a number of chips. One of these is a DC to DC converter, one of them is an analog devices delta sigma converter, and there's a few support chips. There's a charge pump chip and an op amp. So what this is basically doing is it's a kind of a glorified PWM in some ways. I'm still adjusting the wrong controls, so let's just grab this here for a second. Sorry, there we go. Still pressing the wrong controls. What we're looking at here is a 1-bit representation of a 0 current flow, and looking at the data sheet for this particular current sensor, what that means is that when you have 0 current flow going through here, it basically alternates 1 0 1 0 depending on a clock frequency that needs to be applied externally. Now Elon here pumps out a rather impressive 18 megahertz clock to the current sensors. Obviously Brains here hadn't anticipated this particular setup, so in our shiny new logic board we don't have a mechanism to supply a clock frequency. Okay, so also you might say, well, if we've got ourselves a digital signal, how are we going to work that into our design? So whilst this is a digital signal, it is intended to be digital filtered to reproduce a very accurate analog value relating to the current flow along this bus bar. So the multimeter is already doing that. It's basically seeing that we have a 50% duty cycle and is representing this by 2.5 volts. Now right now we're clocking this device at a much lower frequency. I got one of these Digilant Analog Discovery units for a work project, but just figured it'd be a good way to supply a variable clock frequency to this card to do some testing. And I was quite surprised to find that I can actually clock this way down. I can clock it down to about 1 kilohertz. Now, the problem is, as we lower the clock frequency, we lower the amount of data that we're sending. And if we lower the amount of data that we're sending, we're going to lower the accuracy of the current sensor. Now, the thing about this is that the Hubner inverter does not depend on having very accurate current sensing. The current sensing is used in this design primarily as a safety shut-off. So if the current through the motor becomes excessive, we basically shut down. It's not part of the control algorithm. Whereas in the Tesla original logic board, it would be very important to have extremely accurate current measurements of the to have accurate current measurements. So we're going to cheat. First thing we're going to do is we're not going to digital filter it because we don't have the processor horsepower. And in fact, that might explain why there's two pretty serious Texas Instruments microcontrollers on the original Tesla logic board. So we're not going to do that. We're going to go old school. We're going to analog filter it and get our 2.5 volts signal, which varies depending on positive or negative current. And yeah, we're going to reproduce an analog value representative of the current and feed that into the existing circuitry that we have laid out on our new PCB. So we're then going to clock it, and I'm going to clock it at as high a frequency that I can. I might even, on the new rev of the PCB, go and put a clock synthesizer, a clock synthesizer chip in there, and get us a clock frequency. I think that device can clock up to 20 megahertz. So we might reproduce what Tesla are doing and clock us up at 18 megahertz. But need to do some experimentation, so that's what we're going to be doing here. So do stick with us, and let's see what happens as we put this thing back together. I'm going to run some tests here with some simple analog filtering and varying the clock frequency with the analog discovery, and yeah, let's go clock some current sensors and see what happens. Stay with us, it's going to be nerdy fun. Alright, so with a 1 megahertz clock, you can see that the jitter on the voltmeter has calmed down a lot. And if we run some current through the bus bars, I've got a 10 amp power supply here, you can see the operation of the current sensor. current on, current off, current on, current off. So the higher we can get the frequency, the more data we're going to be able to gather. Alrighty folks, so when we were last talking there was about the Delta Sigma modulators on the Tesla current sensors. So what I've gone ahead and done is I put the prototype logic board on here, and when I was designing this, it should be easier to show you on one of the bare boards here. I had brought out what I thought to be the reference voltage pins from the current sensors to a little 4-pin header here. So I brought out the two signals and a ground and a 5 volts. And what that enabled me to do then, take a little Arduino, I think this is an Arduino Nano, just put a few lines of machine code on that, or assembly code, sorry. So that's putting a 1 megahertz clock now into our Delta Sigma, or Sigma Delta, I can never forget which, I can never remember which, modulators on our current sensor. And that's running them, and we were able to change just two little capacitor values on there, and we're getting a nice analog ratiometric signal now from the current sensors, which is compatible with our control board. Now you might see here that I have an FTDI lead plugged into the board. That is simply for communication at the minute, because the pins in the 23-way amp seal that I had allocated for RS232 inside this little board here, a lot of little filtering components and so on, and unfortunately there's a little 47 nanofarad capacitor across them, so my RS232 didn't quite work out, so I'm going to have to reassign the pins in here. I'll do a little bit more checking on this board so that I can avoid whatever pins have those capacitors on. So the board is running away here. We're supplying 12 volts to it from bench power supply. We can see it's got the 5 volt light on here, and our little heartbeat light from the microprocessor. Everything else on the board is working perfectly. It's talking to all the various parts of the Tesla inverter so far. We had one other problem, which is a little bit of a strange one, that when I actually got it working, I couldn't raise the DC bus voltage above 19 volts or the inverter shut down. So what that turned out to be is I made a pretty amateur mistake on here when I brought the signals in from the IGBT driver boards, in that I didn't put a little filter on the fault lines coming in from the IGBT driver boards, and so there's little pulses on that from the transistors switching, very narrow now, about maybe 30 nanosecond pulses, but they were being brought in through the fault lines and been brought straight into our 74HC30 NAND gate, and that was fast enough to cause a shutdown on the microprocessor. So you see a few little components here, made a little simple low pass filter there that's getting rid of those spikes for me. Now when we do the next version of the board, we've got quite a few things to change. The power supply is going to change a little bit, because there's no point having a 3 amp power supply here. Like, the whole logic board barely takes 100 milliamps, so it's a much smaller power supply section that we can do here. I'm going to put a transparent latch on the drive signals from the microprocessor to the IGBT drivers. because we want to basically just buffer them up to 5 volts, so we can you know, have a bit more drive going into the driver board. Yeah, I'm not making much sense today, sorry guys. So anyway, yeah, we got a few good mods to do, but you know, the point of this is, you know, this was never going to be the perfect card. This was going to be enough so that we could find what we would need to do to modify it. But I have to say, it's just been working out very well. So anyway, let's do a quick little demonstration here. So I have power supply setup supplying about 40 volts onto the DC bus here. And I have a little, just a one horsepower industrial motor just connected to the inverter here, just for purposes of kind of demonstration. So I'm going to go ahead and let me just start the inverter up. Now currently we're set to 8.8 kilohertz switching frequency. And so we're spinning the motor up to 25 hertz now, and you can probably hear there's a there's a fairly significant whine coming from the inverter at that particular switching frequency. And we're drawing, if you look at our power supply, I don't know if you're going to be able to see it, but we're drawing about 1.4 amps currently from our 12 volt feed. Now if I stop the inverter here, and if we change our switching frequency on the computer, let's see, where are we? So we can select a few different switching frequencies. 8.8 kilohertz is the default. You know, we can do some silly ones like 1.1 and 2.2. We can do 4.4 kilohertz, but we can then do 17.6 kilohertz. So let's go to 17.6 kilohertz. Now we've set that, and let's start inverter there now. So basically now we're spinning up at 17.6 kilohertz. There is no whine from the inverter, but we're now drawing about 3 amps, a little bit less than 3 amps of current from our 12 volt feed. So I suppose that is probably because we are switching the IGBTs kind of twice as frequently at that switching frequencies. Yeah. So anyway, I guess this is kind of a demonstration of our first iteration of our open source logic board for the Tesla inverter. A couple of more iterations of this to go, but I think what I'm probably going to do is I'm probably going to spin the Tesla motor with this fairly soon and check that we can read the encoder. But this is, this is a start for now. Sorry, I'm a bit zoned out at the minute, guys. I've just got a lot of stuff going on, but I still wanted to make a video to show this to you, and just to show that we are making a lot of progress here. So righty then. I hope you enjoyed that. I guess the next episode, hopefully I'll spin the Tesla motor itself with this particular setup, and then we will do the modifications to the PCB, and we will get the next batch of PCBs made. And I would imagine that the next iteration of this should pretty much just work out of the box. I suppose
you know, some people don't quite believe in this method of design, but it's just the one that I've kind of gone with for a long time now. I find that you just tend to get a better end product out of the thing, and I'm hoping that'll be the case here. Just as of note, I have published the design of this particular board for people, purely for kind of educational purposes to see. I'll put a link into the description for my GitHub page. So that's it for now, guys. As I said, sorry I'm a bit zoned out. Just had a lot of crazy stuff going on, and my health has been a bit weirded out as well. So yeah, thanks for all the support and stuff, and I will see you back in the next video. Don't forget to subscribe and leave a like, and happy Delta forcing.